from the homework, we start off with an alcohol, right? And it's saying, what did this come from? Right? What are the starting materials? They actually gave you options here, but I'm not gonna give you the options. It's like a fill in the box thing. But for this, essentially, we gotta distinguish what kind of functional group we have here. So what kind of functional group do we have here? An alcohol, that's a tertiary alcohol. So it's a tertiary alcohol. Well, not necessarily. So let's be careful with this, right? So it's a tertiary alcohol. That ketones, so tertiary alcohols can come from two places. They can come from ketones, right? Generally speaking, not this ketone, but ketones. What else can tertiary alcohols come from?
Secondary aldehydes? No?
Esters, like a generic ester. So the key here is how do you distinguish whether or not it came from one or the other? The key to knowing this is when you have a tertiary alcohol, if the alcohol, if it's tertiary and has three different things bonded to that carbon, right? See how this is a methyl, this is a ethyl, this is a 1, 2, 3 propyl group. It couldn't have come from an ester. Because remember, esters react with two equivalences of Grignard, the same Grignard, right? Whereas ketones, right, can start off being unsymmetrical and then be reacted with one of these Grignards. So let's just go through, let's just pretend, so if I wanted to do, right, so let's just go with this ester. Let's say it's my starting material. What Grignard would I have to react it with to get this product? Is it possible to get this product? So I have a methyl, so I don't have to use that Grignard. What Grignard should I use?
CH2, CH2, CH3.
I'll use the propyl Grignard, okay. So we're going to use the propyl Grignard. MgBr, right? Now, don't forget all the ways to put bromine on molecules, put bromine, anti-Markovnikov, all those good things, right? You can come back to the questions and these kind of things, right? So we have a Grignard. This Grignard is going to react, right, with the carbon of the carbonyl group, right, the electrophilic carbon of the carbonyl group. You get O minus, right? We have a tetrahedral intermediate. Once you have a tetrahedral intermediate, you always ask yourself, well, right, is it going to stay this way or is it going to collapse? In this case, is there a good leaving group? The O minus can leave, right? So we bring those electrons down. Good. Right? But now we've made a ketone, and what's more reactive, a ketone or an ester towards nucleophilic addition? Which carbon's more electrophilic, a ketone's carbon or an ester's carbon? What's more electrophilic? What's more electrophilic, this carbon or this carbon? Why the ester? Right, so one way to think about it is, right, this is pulling away oxygen, right? But the other thing to think about, though, is can this do resonance? Right, remember, if you can do resonance, you're going to be more stable. So your logic isn't wrong by saying, oh, it's pulling away electrons. That's not wrong logic. But the most important part is actually the resonance. So resonance is more important. So esters are less reactive than ketones and aldehydes, right? So if you can do resonance, you're going to be less reactive. So we have a ketone, now it's more reactive, and we probably have some leftover, or there's probably some, right, Grignard still floating around, especially since the product we make is actually more reactive than our starting materials. It's going to react pretty fast. I'll go up this way, sorry. Right? And then we'd finally treat it with H+, right? Step 2 always. Then we make the alcohol, right? But again, is this the right product? No. So remember, with esters, the same Grignard adds twice. So if you want to put 3 different carbon groups on, make a tertiary alcohol, you can't start with an ester. It has to come from a ketone. Does everybody see that? Let's look at taking a benzoic acid and reacting it with SOCl2. So just like we did in the quiz actually the other day, or the part of the quiz we got tested on. I think did I have pyridine in there as well? Did I put pyridine in there?
I think maybe you did.
I might put let's put pyridine in there, why not?
I know there was a homework problem that didn't have it.
Yeah, I mean, you don't necessarily need to have it. It just helps move things along. So, in this case, right, we know at the end of the day, right, this carbon of the carboxylic acid will be the electrophile. But at first, right, are carboxylic acids very good electrophiles? No, because they'd have so much resonance, right? So remember SOCl2, you remember that from activating alcohols? We could turn those alcohols into chlorines. So we're going to do the same exact thing with this carboxylic acid. We're going to turn it into an acid chloride. So to do that, this guy attacks, we kick up, right? We get tetrahedral intermediate. These are neutral conditions right now. Pyridine is a little bit basic, slightly basic, but really at the end of the day, it's more or less neutral. I mean, I think we'll make some acid, but balance our charges, right? All right, so it's very similar to what we did in chapter. Well, I don't know what was it. The chapter with activating alcohols. We'll take the proton.
Does it matter here in the order?
It doesn't really. I just do this to balance the charges out usually. So again, the sulfur got attacked, and the sulfur, remember, is just one row below carbon, so it's very similar to carbon. So this is went from sp2 to sp3, so a tetrahedral intermediate. Tetrahedral intermediate, we ask ourselves, right, do we have a good leaving group? And we have a good leaving group here. Either chloride would work. We kick those out, kick one out. And then remember, don't forget, at the end of the day, what we were trying to do, right, we wanted to turn this OH into a Cl. Right? And so remember, the only one, people forgot this, the only one that doesn't do an SN2 is tosyl chloride, right? So this is going to re-attack. The chlorine's going to attack here, going to kick up. All right. So now at this point, people would say chlorine is a better leaving group maybe than O minus, even if there's resonance. But let's just say every once in a while this happens, and it comes down. These electrons go to here, and we create SO2, which is a gas, right? And then chlorine gets kicked out too. So the same exact mechanism as we did before. You guys have seen this, right? So at the end of the day, we've made an acid chloride. Dr. Wenzel, please, not Jesus. SO2, right, which is a gas, right? So that drives equilibrium, right? If we have a gas, there's no going back. So really, this arrow should be a one-way street arrow, right? Because SO2 bubbles out of the solution. We're not going back, right? We also make Cl minus. But now we've turned, right, this is that cool, remember we talked about Umplong chemistry, right, with Grignards, taking a alkyl halide that's electrophile and turning it into a nucleophile Grignard. We took a carboxylic acid that's not very reactive, not very electrophilic, and now made it very reactive, made an acid chloride. Right, some of you guys did this, and some people did this for Keck, obviously, too. All right, this is still going over the quiz from the other day. Plus H, N, it's an H. All right, we have 1 mole of each. And the confusing part of this problem was actually the moles, like thinking about the moles. So the way I drew it for one class, I didn't do this with the 9 o'clock class, but I drew it basically saying, imagine you have, right, this is in your beaker. Right? So molar just means like a 1-to-1 equivalence, right? So if I have 10 acid chlorides, I have 10 amines. That's just, moles just means equal amounts of molecules, right? So this mechanism though requires, so again, electrophile gets attacked by the nucleophile, comes up. L minus, Cl, N, H, and plus charge. So the problem here is, at the end of the day, probably at this point, or maybe at a different point, another mole of this amine is going to come in. Because amines are strong bases, or decent bases, right? We could say proton transfer here, but the amine's probably going to help move that proton around. Actually, I take that back. Let's not do that right now. I'm calling it off. Let's just do a proton transfer. Why mess around, right? We're saying proton transfer. The proton that I just erased right here, this proton is going to get transferred to that negatively charged oxygen.
Eventually it'll do that if you didn't do that.
There's enough molecules in, sure. They'll probably get shuttled around by an amine, but whatever. Again, you have a...
Isn't that cell chlorine?
Oh gosh, I'm all over the place. That's right. Now, tetrahedral intermediate. What's my best leaving group? It's going to be the chlorine. Electrons come down. Kick that guy out. So people say, "Oh, there's Cl minus around." There will be Cl minus around. But even if you had Cl minus attack and take the proton, right? What'd you just make? HCl is what kind of acid? So strong acids are going to react with bases, right? Well, what if I have HCl sitting here, and I have an amine sitting here? They're not just going to look at each other; they're going to react, right? So what that means is in this mechanism, because I generated strong acid, one of my starting materials is going to react with that, right? Alright, so I make a nitrogen with two H's on it as a plus charge. Alright, so if you look at this mechanism, the key point here is if you look at this mechanism, how many molecules of amine are involved in this mechanism? Two. For every one of these that reacts, two of these react, right? So if you look back to our beaker, this guy's going to react to get the product. Two amines are going to have to react for every one of these. So what do you have left over? You have left over acid chloride. You see that? There's always going to be leftover starting material because, right, according to the mechanism, for every two of these, I only react with one of these. So I'd have, right, if 1 mole of these react, I'd have 0.5 moles of the starting material left over as well as 0.5 moles of this product.